Last time in separations, we discussed single-stage batch distillation, aka the Rayleigh still. Today's topic extends that idea to now multi-stage batch distillation. For multi-stage batch distillation, the main ideas are the same, except now instead of just a pipe that is above the reboiler, there's now a distillation column. So in the process flow diagram that I've sketched out already before the video started, I have a five-stage distillation column. And this column can be as many stages as you want. Typically, again, one of the main specifications that you'll make as an engineer is how many stages do you want your column to have. So before I start, like I said, this is the main diagram. Really, the only difference from before is that I now have a column, so I need some reflux. I need some liquid going back into the column at the top. So I've got a total condenser. I've got a reflux ratio. I'm going to start filling in some notation here. R is going to equal L0 over D, where L and D are going to have the same meanings that they did in continuous distillation. And actually, I'm going to make a small change. I'm going to call D D dot now. For a flow, this is going to denote that there's a flow rate going on. And that is very important because in batch, remember, we're keeping track of overall amounts, not necessarily flow rates. And also from single stage batch distillation, remember that D was just the overall amount that was going into the overhead product. Remember, this is called the overhead, and because it's being collected in some sort of vessel here, I'm going to call it D total. And that's kind of the best notation that I can think of for the overhead. All right, so it's D total is the accumulation of all the D dot that is flowing into this over time. The bottom's product is still going to be B at a composition XB. I also forgot that we need another variable for D. So we're going to call it, let me see what I called it in my notes. I'm going to call this XD average. And it's not technically an average, it's just a reminder that this is the accumulation of all the XD that's flowing into this once again. So a little bit of different notation. Once again, don't try to memorize the formulas. Think about it, and I'll walk you through how I'm thinking about these things. B at time 0 is still going to be F. B of time 0 is equal to F, and XB at time 0 is equal to Z or XF. Once again, I use those interchangeably, not on purpose, but sometimes I've got different notations. I'm going to try and stick with Z because I think that's easiest in the context of what we know so far. Okay, so the analysis is pretty similar. We're going to do material balances, and importantly, I'm going to assume when I'm doing my material balances that there's no accumulation or holdup anywhere in the column. So what this assumption means is that the instant that a bubble of vapor forms in the reboiler, it is instantly going to go, teleports basically through all these 5 stages through the condenser and either gets recycled or into the overhead, condensing almost instantaneously. So another way to think of it is that there's no material on any of these stages. And of course, this is unrealistic, but this is the only way that we can perform an analysis on the overall column. So the material balances is going to follow pretty much the same as it did from, it's kind of a mixture now between continuous distillation and for single stage batch. So if I just take the top of the column, so if I take the first N stages, say, maybe the first 3 stages, and I encapsulate the condenser and the mix point, what will my balances look like? Remember, I've got V and L flows in the column, and I'm going to assume constant molar overflow such that V is equal to V throughout the column, L is equal to L throughout the column, and I'm putting dots in, again, just to clarify that these are flow rates and not amounts. So the overall material balance is, once again, F is equal to D total plus B, and ZF is equal to XD average times D total plus XB times B. And then because we need some more equations here, so if you remember in the Rayleigh equation, we did a differential balance inside the column. I'm going to do something similar. And this is kind of where we draw the analogy to the continuous process. So if I drew this square here with the dotted lines encapsulating the top few stages, I'm going to be able to do a material balance in kind of the same way that I did for the whole column. So this is again an integral balance, integral overall balance, and these are going to be differential top n stages balance. This is going to help us derive the other equation that we'll need. So once again, of these 6 variables, we'll need 3 of them. So typically we'll know what f and z are, and we'll have one more specification out of xd average, d total, xb, and b. So differential top n stages balance would look like this. I have v dot coming in from stage n plus 1, and that is equal to L dot of stage n plus D. And I also have V dot from stage n plus 1 times the composition of that, so Y of n plus 1, so this is the vapor phase composition of the more volatile component, is equal to L dot n times xn plus xd average times D. Nope, not xd average. I mixed it up. xd, all right? Remember, these are in general different. xd times d, and I'm going to put that in a star and in red. xd is different than xd average. All right, and I think I'm going to have a homework problem, especially asking you to plot both of these as functions of time so that you see how different they are. Okay, so given these 2 balances for the differential top n stages, you can once again rearrange them. And I'm going to skip a couple of steps, but I encourage you to work this out on your own so that you can prove to yourself that you can do it. It is going to be L over L plus D times xn plus D over L plus D times xd. And once again, if we define the reflux ratio, R, to be L over D, then I'm going to be able to substitute and say y of n plus 1 is equal to R over R plus 1 plus 1 over R plus 1 xd. So this is my operating line, and it has the same meaning and equation as it did for continuous. Same meaning and equation as before. All right, now this is all good, but still not enough in order to be able to calculate what we need to. So in order to do that, we're going to have to derive the analogous form of the Rayleigh equation. So I'm going to take a different balance now, and instead I'm going to draw a gold border around the entire column such that I can derive my differential Rayleigh equation. So this is Rayleigh equation for multistage. And remember before we were talking about accumulation. So this is going to be the link between the batch type part of the process and the continuous part of the process. I think part of the confusion that people have with this is that it's overall is a batch process because nothing's entering or leaving. But if I just look at any particular stage of the column, it's continuous within that batch process. So once again, the Rayleigh equation is that link between them. So I am going to say that the accumulation inside the reboiler, that's dB dt, is equal to, so at what rate am I losing stuff from the reboiler? Well, as stuff leaves, remember I'm imagining that as soon as it evaporates, it's going through the column, through the condenser, through the split point, and into the overhead products. So the rate at which material leaves the bottom the reboiler is going to be equal to the rate at which d dot flows into the overhead. And it's minus d because it's flowing out. Right, and I could do a same balance on the more volatile component. So dxb times b dt is equal to minus d times xd. And then the derivation from here is exactly the same as it was for the Rayleigh equation. So I'm going to product rule this derivative, and I'm going to plug in dB dt for d dot. And eventually, I'm going to get down to this equation. ln of, sorry, I keep doing that. I keep mixing up w and b. So in my notes, if I ever write w and you're confused about what w is, that's the same as b. That's what I used to call b. That's what some other textbooks refer to b as. So ln of the bottoms over the feed is equal to the integral from xf to xb, did it again, of 1 over xd minus xw xb, keep doing it, d xb. All right, so practice deriving this Rayleigh equation, again, doing the same steps I did. So again, product rule to distribute this differential term, plug in dB dt for minus d dot, multiply through, remember in quotations, multiply through by the dt, and then separate variables and integrate. Now the problem with this Rayleigh equation, so this is not necessarily usable just yet. I cannot integrate this right-hand side because xd is a function of xb. Integrate. xd is a function of xb. In other words, as the composition in the reboiler is changing, xb is a function of time. Therefore, xd is going to be a function of time. And these two things are going to be related, but the relationship is not immediately clear. So remember, in single stage batch distillation, we said that the relationship between what is leaving in the pipe was y. The relationship between y and xb was that they were in equilibrium. That is not true anymore because there's stages of the column in between xd and xb. So the main problem with this equation is that I need to know what the relationship is. xd is a function of xb, but the relationship is now unclear. It is unclear. They are not in equilibrium. And that is because there are stages of the column in between. All right, so that's going to finish up this video. In the next video, I'm going to talk about how to get this relationship between xd and xb such that you can perform this integration. And this Rayleigh equation for multistage is going to be the third equation that you need in conjunction with the other two, which are my overall material balances, overall integral material balances, in order to find 3 of the unknown variables. So I'll see you in that next video.